Up to this point, you should have learned how to take the derivatives of various types of functions, including polynomials, products, natural logs, and more. But how would we go about taking the derivative of something like this, where one function is nested inside of another? In this video, I'm going to show you how to apply the chain rule for problems such as these. Before we get started, let's briefly review composition of functions. Composition of functions can be described as nesting one function inside another, and is usually denoted with a little circle between the two functions. For example, if f of x equals x cubed, and g of x equals 8x minus 2, then we would say that f composed with g equals the composite function f of g of x equals the quantity 8x minus 2 cubed. To compose one function with another, it's helpful to write them in nested form, like this, f of g of x. From here, we can replace g of x with 8x minus 2, which gives us f of 8x minus 2, and plug that in everywhere we see an x in the function f of x. In a similar way, we could write g composed with f as g of f of x equals g of x cubed, which is 8 times x cubed minus 2. The chain rule is a method which helps us take the derivative of nested functions like f of g of x. It states that the derivative of a composite function like f composed with g is equal to the derivative of the outer function composed with the inner function, and this is multiplied by the derivative of the inner function. Another way of expressing the chain rule is by writing the derivative of the function f composed with g is equal to f prime of g of x times g prime of x. So if we wanted to find the derivative of f of g of x, we would first write the derivative of the outer function, the cube, while leaving the inner function alone. Given that f of x equals x cubed, then f prime of x equals 3 times x squared, and f prime of g of x equals 3 times the quantity 8x minus 2 squared. Then multiply this by the derivative of the inner function, 8x minus 2, which would be 8. As a result, the derivative of the function f composed with g is equal to 3 times the quantity 8x minus 2 squared times 8. This can simplify to 24 times the quantity 8x minus 2 squared. Now we could have handled this derivative by expanding out the quantity 8x minus 2 cubed and then applying the power rule to the resulting polynomial. However, this expansion would have been time-consuming to calculate. Once you get the hang of the chain rule, you'll find that it's an excellent time saver in problems like this. Let's work through another example. Use the chain rule to find the derivative of the function h of x equals the square root of the natural log of x. First, let's identify what the outer and inner functions are. Since the natural log of x is nested inside the radical, it is the inner function, while the outer function is the square root. The chain rule says that the derivative of a composite function is equal to the derivative of the outer function with the inner function untouched times the derivative of the inner function. Since the derivative of the square root of x, or x to the 1/2 power, is 1 over 2 times x to the negative 1/2 power, we write the first part of the derivative as 1 over 2 times the quantity of the natural log of x to the negative 1/2 power. Then, multiply by the derivative of the inside. Since the derivative of the natural log of x is 1 over x, we will multiply by 1 over x. Simplifying, we get that h prime of x equals 1 over 2x times the quantity of the natural log of x to the negative 1/2, or 1 over the quantity 2x times the square root of the natural log of x. Let's do another example. Use the chain rule to find the derivative of the function j of x equals e raised to the quantity 8 times x squared. This function may look a little intimidating, but we have the tools necessary to work through its derivative. In this case, the outer function is the exponential function e raised to a power. The inner function is that power 8 times x squared. To get the derivative with the chain rule, we need to first write the derivative of the outer function with the inner function untouched. Since the derivative of the outer function, e to the x, is itself, we're just going to write e to the quantity 8 times x squared again. Then, we need to multiply this by the derivative of the inner function. Since the derivative of 8 times x squared is 16x, let's go ahead and write that down. This simplifies to 16x times e to the quantity 8 times x squared. Not so bad, right? Now I want you to try a problem on your own. Using the chain rule, find the derivative of k of x equals the quantity x cubed minus 9 to the 11th power. Remember, you'll need to handle the outer function's derivative first, then the inner function's derivative. Pause the video to work out the answer for yourself. Let's check your work. What is the outer function? In this problem, it's the 11th power. The inner function is x cubed minus 9. The first part of the chain rule dictates that we write the derivative of the outer function with the inner function still inside of it. So we will have 11 times the quantity x cubed minus 9 to the 10th power. Then we are going to multiply this by the derivative of the inner function, which will be 3 times x squared. If we simplify this, we'll get k prime of x is 33x squared times the quantity x cubed minus 9 to the 10th power. This problem, like the first one in this video, could have been solved by expanding the polynomial to a 12-term expression and then handling each term individually with the power rule, but I think it's safe to say that the chain rule is a much better method for finding this derivative. Let's work through one last example. Leo is studying population growth in a petri dish of mold spores. The dish starts out with only one spore, but the spore duplicates itself, and there is exponential population growth over time. If the number of mold spores on day x can be calculated using the function m of x equals e to the square root of x, determine the function m prime of x, which represents the growth rate. Because we are interested in finding a rate function, m prime of x, we understand that this is a derivative problem. And since the function m of x is a composite function, we know that we are going to need the chain rule to find that derivative. The outer function in this case is the exponential function, e raised to a power. That power, the square root of x, is the inner function. To find m prime, we start by taking the derivative of the outer function while leaving the inner function as is. Once again, the derivative of e to the x is itself, so we will start by just writing e to the square root of x again. Next, we have to multiply this by the derivative of the inner function. Since the derivative of the square root of x is 1 over 2 times x to the negative 1/2 power, the growth rate function m prime is equal to e to the square root of x times the quantity 1 over 2 times x to the negative 1/2 power. Or equivalently, e to the square root of x over the quantity 2 times the square root of x. Remember, the chain rule helps us take the derivatives of composite or nested functions. To get these derivatives, first write the derivative of the outer function with the inner function still untouched within it. Then multiply this by the derivative of the inner function. This technique will come in handy anytime you see a function contained in another function, whether under a radical, in a logarithm, or even inside a trig function. As always, a little practice goes a long way, so I encourage you to try some problems on your own. Thanks for watching and happy studying.